Atoms are the fundamental building blocks of matter, forming everything we see and experience in the universe. In this note, we will delve into the fascinating world of atoms, exploring their structure, properties, and significance in understanding the physical world around us. Atomic structure: atoms are incredibly small, with a diameter on the order of 0.1 to 0.5 nanometers, 10⁻⁹ meters. They consist of three main subatomic particles: protons, neutrons, and electrons. Protons carry a positive charge, neutrons are electrically neutral, and electrons have a negative charge. The nucleus, located at the center of an atom, contains protons and neutrons tightly bound together. Protons determine the atomic number, defining the element itself, while the sum of protons and neutrons gives the atomic mass. Electrons orbit the nucleus in energy levels or shells, and their arrangement determines the chemical properties of an element. Atomic models: throughout history, several atomic models have been proposed to explain the structure of atoms. The most notable models include the Thomson model, Rutherford model, Bohr model, and the modern quantum mechanical model. Thomson model, proposed by J.J. Thomson in the late 19th century, this model described atoms as a positively charged pudding with negatively charged electrons embedded within it. Rutherford model, developed by Ernest Rutherford in 1911, this model suggested that atoms have a tiny, dense, and positively charged nucleus at the center, with electrons orbiting around it. Bohr model, proposed by Niels Bohr in 1913, this model built upon the Rutherford model and introduced the concept of electron energy levels or shells. Electrons were thought to occupy specific energy levels and could transition between them by absorbing or emitting energy. Quantum mechanical model: the modern understanding of the atom is based on the principles of quantum mechanics. According to this model, electrons are described by wave functions, and their behavior can be understood in terms of probability distributions known as orbitals. Properties and behavior: atoms exhibit various properties and behaviors that govern their interactions and chemical reactions. Atomic mass and atomic number: the atomic mass of an atom is the sum of protons and neutrons in the nucleus. The atomic number represents the number of protons, defining the element. Electron configuration: the arrangement of electrons in energy levels determines an atom's chemical behavior. Electrons occupy specific orbitals within the energy levels, following the Pauli exclusion principle and Hund's rule. Isotopes: atoms of the same element can have different numbers of neutrons, resulting in isotopes. Isotopes possess the same atomic number but different atomic masses. Valence electrons: the outermost electrons in an atom's electron configuration are known as valence electrons. These electrons play a crucial role in chemical bonding and determining an element's chemical properties. Chemical bonding: atoms can form chemical bonds with other atoms, leading to the creation of molecules and compounds. Bonding can occur through various mechanisms, such as ionic, covalent, or metallic bonding. Quantum mechanics: the behavior of electrons within atoms is described by quantum mechanics, which introduces concepts like wave-particle duality, uncertainty principle, and quantization of energy levels. Significance and applications: understanding atoms and their behavior is essential in numerous scientific and technological fields. Chemistry: atomic theory forms the foundation of chemistry, explaining how elements combine, react, and form compounds. Materials science: knowledge of atomic structure and bonding is crucial in designing and developing new materials with specific properties. Energy: understanding atomic reactions and nuclear energy enables the development of nuclear